It's part of our attendance procedures. And we will ask at the end. There's also a short quiz, 3 questions like we do, but we need you to be present and document it in the chat window, so that we have that record and can submit the information to the New York State Council, who curates all the records. So when you renew your PG license, if the state wants to verify that you're claiming that you have the adequate number of credits, that's where they go. Also, I mentioned earlier in the chat window in a note, there looked like there were a couple people that were signed in just as iPhone or iPad. And if you're one of those people, we need you to tell us that you're here and just say I'm iPad and it's, Jimmy Johnson. So, and I think that's about it. Jennifer, did I miss any housekeeping items here?
I think you got everything.
Okay, great.
Oh, I'm sorry, one thing. If you need any questions, if you have any questions during the presentation, maybe a clarification on something that Bob says, please feel free to speak up and we'll address that during the presentation. Otherwise, you can hold all comments to the end.
Okay, with that, I'm stopping sharing and I'm going to let Dr. Much, I'm going to introduce Dr. Much, our distinguished speaker this evening, and he's got a great talk on aquifer testing and fractured rock, and we really appreciate him devoting the time to do this for us. We always try and keep the content varied and interesting so that we learn things. So with that, take it away, Bob.
All right, well, thank you, Chris. Can everybody hear me okay?
Yes.
Okay, good. Yeah, I'm a groundwater hydrologist, and I think there was some bio information presented, but I've been in the consulting field for 40 some years and taught at Manhattan College and Columbia hydrogeology. And I wanted to discuss something close to my heart, which is aquifer testing in fractured rock, and with particular focus on methods that rely on hydraulic diffusivity, so specific measurement of hydraulic diffusivity. And also maybe we'll take a look at how we can do tracer tests very kind of inexpensively during the course of aquifer testing. So I'll touch on these hydraulic diffusivity-based methods. One of the earliest method based on hydraulic diffusivity was the Neuman and Witherspoon ratio method, which goes back to like 67 or something. And more recently, the Hsieh crosshole technique, which is actually not particularly recent. It was actually developed in 1985, but it has gotten fairly light use in the industry. So we'll talk particularly about that method, and we'll touch on tracer testing, and then just see where we're heading with all this. And, so hydraulic diffusivity, it's basically the property that governs the rate of pressure wave propagation in a geologic medium. It's usually defined as alpha prime. And it, as shown here, it equals the directional hydraulic conductivity divided by specific storage. And that's kind of makes sense. The higher the hydraulic conductivity, the higher the pressure wave travels. And it's also inversely proportional to the specific storage, which is acts kind of like a dampening function to slow the rate down. Once you have hydraulic diffusivity, which a number of these methods can give you, you can readily convert that parameter to directional hydraulic conductivity simply by multiplying by specific storage. But you do have to define specific storage independently using some other methodology. Unlike some more conventional aquifer testing methods like the Tice method and Cooper-Jacob and things like that, we have to define specific storage independently. So I mentioned the Neuman and Witherspoon ratio method, and this is applicable to a very particular set of hydrogeologic conditions. You need to have an aquifer within which you have a monitoring well, but you're really looking at the rate of propagation of drawdown from the aquifer vertically, typically, through the aquitard. And that can either be upward or downward, depending on where your piezometers or monitoring wells are. So you do need that hydraulic conductivity contrast. So this would be an example of a typical ratio method setup where you have a pumping well in the aquifer and you have several monitoring wells, all roughly at the same radial distance, but screened at different vertical locations. So it might look like this, where we've got an upper water-bearing zone, we have an aquitard of some thickness, and then a semi-confined aquifer. So the pumping well is screened in the aquifer. There needs to be at least one well also, monitoring well screened in the aquifer. And then the idea is you would have additional monitoring wells or piezometers that are screened across the aquitard so that you can measure and define the propagation of drawdown vertically upward through that aquitard. Once the drawdown reaches the upper piezometer, which is screened right near the top of the aquitard, the test is basically over. At that point, you start to get leakage in from the upper aquifer, and it becomes more complicated. So what the idea is, what's going to happen when you start pumping this well is drawdown is going to spread very rapidly, as you see here, in the aquifer. So you're going to get very rapid drawdown in the aquifer monitoring well, and then you'll begin to see the vertical propagation as time goes on up through the aquitard until you begin to see drawdown up at the top of the aquitard. That's why they call it the ratio method, because you're looking at the ratio of drawdown in the aquifer to drawdown at various times in these aquitard piezometers. So here's this is just an example of an actual test. This was done in Jersey City in the Passaic Formation. The upper rock zone, the URZ, is shown here as the blue line. So that obviously begins drawdown rapidly up to close to 20 feet of drawdown. And then we have a series of 4 additional monitoring wells that are at greater vertical depths in the rock. And the distances are given here. But you can see that each well in turn is subject to drawdown as the drawdown propagates downward, in this case, through the lower permeability rock. And just quickly here, we're calculating hydraulic conductivities of different depth intervals, ranging from roughly 10 to the minus 5 centimeters second down to 2 times 10 to the minus 6 centimeters per second. So kind of as you would expect, you're seeing a reduction in hydraulic conductivity with depth as you get into the deeper rock. This is another more recent test that was done out at a site in Pennsylvania. This just shows kind of a generalized cross-section where all the wells are screened. The actual pumping well is shown here. If you can see my cursor, PW3. And in this case, there's a high K zone in this rock that's actually about 500 times more permeable than either the overlying or underlying rock. So when this well pumps, drawdown propagates out very rapidly in this roughly 75-foot thick high K zone. And what you're seeing here actually enumerated alongside the open intervals of this rock is the amount of rebound that occur. This is actually a well shutdown test. So the well was pumping for several years at like 42 gallons a minute. And we rapidly, turned it off and recorded these rebounds, which we have in more detail, but this shows the magnitude of the drawdown. We had 10, 14, 11 feet of rebound, and we can see how that propagated up a little bit into the rock. We've got 2 feet, 1.5, some pretty, in a lot of cases, non-detect, going up into this lower permeability rock. Just to show you what these tests look like, and I won't go through this in detail, but this is an example of the plots from two wells, and really two wells of interest in particular. This well right here, which shows the 14.4 feet of rebound. That's a D series well. And then there's a companion well up here, which is part of a well cluster, which is well B in particular. There's also a well C, which is intermediate. And so we're looking at drawdown that propagated out laterally from the pumping well to this well, this D well in the cluster, but also vertically upward into this significantly lower permeability rock. And here's how those plotted. So the gray plot is the deep monitoring well, and the shallowest well is the B well, which is down at the bottom here. And what we're doing is we're looking at the ratio between the drawdown that was observed in the D port, which is in the high permeability zone, and the drawdown that's occurring in this upper part of the aquitard. And then I'm not going to go take you through this whole calculation. Suffices it to say, Neuman and Witherspoon recommend you do 2 ratios, average the results, and then you end up calculating the vertical hydraulic permeability of this lower permeability rock, which comes out to 2 times 10 to the minus 6 centimeters per second, which is about 500 times lower than the high K rock. This is another test that was done using a different well cluster. I'll just go back for a second. We used this well, 7D, which is right in the high K zone. And then this well, VTBRW01S, which is just up into the lower permeability rock. And I'll skip ahead. So there we have the gray is 7D, which is right in the high K aquifer material. And then up in the aquitard, we can see we got significantly delayed drawdown with ratios calculated here, and ultimately calculating down in the lower left here, the hydraulic diffusivity, and then in the right here, converting that to directional hydraulic conductivity. In this case, it's vertical permeability. That comes out to 1.5 times 10 to the minus 6, which is, I think, remarkably similar to the other well cluster, which came out at 2 times 10 to the minus 6. So that's the Neuman and Witherspoon ratio method, which has been around a long time, but requires very particular conditions to work. The Hsieh crosshole technique is much more flexible. It really can handle a wide range of hydrogeologic conditions. The idea there is that you have multiple wells. Let's assume this is a bedrock environment. So you have wells at all different depths and orientations. And you would conduct actually fairly short-term pumping tests. Just pumping one well and monitoring drawdown in the other wells to see how fast it's moving out from the pumping well, and then do multiples of these. Each one is generating, a lot of data. So if you end up with 5, 6, 10 different pumping tests, you're getting a wealth of data. And the problem then becomes, how do we deal with all that data, and how do we interpret it? One of the things you would look for is whether you're seeing evidence of, like, for example, vertical anisotropy, so that you would have an ellipse of hydraulic conductivity in a cross-sectional view, or possibly both have a ellipse of hydraulic conductivity in the vertical direction, and possibly in the plan view direction as well, so that totally you would have an ellipsoid of hydraulic conductivity, which the semi-axes of the ellipse are the square root of the hydraulic conductivity in that particular direction. So you might have that, but only if the rock exhibits that particular behavior. What I found is most useful is monitoring all of the bedrock monitoring wells, and then observing how that drawdown spreads out. For example, this is just conceptual, but in this case, it's showing a case where it's spreading out rapidly in one orientation, and much more slowly at an orthogonal angle to that. And it's giving you a sense of the three-dimensionality of this bedrock aquifer, where we have apparently a high permeability zone that dips, in this case, to the right. But then we have lower permeability rock on either side, through which the drawdown is spreading out much more slowly. And we might end up concluding that we have this high K zone that's on a dip or an angle, which may well match regional slope and dip of formations, and then we have this lower permeability rock. So a lot of times you may not get an ellipsoid per se, but you may find out the three-dimensionality of the aquifer. So I'll show you an example of a site. This is from New Jersey. This is near Chester, and it's in an area of faulted and folded Precambrian gneiss and Cambrian Hardyston quartzite and Leesville limestone. And there's a site where approximately where this red rectangle is shown, which is right in the middle of this. So the bedrock geology here is fairly complex, but like a lot of sites, the faults are oriented in a northeasterly direction. This is the actual site. There are actually about 25 bedrock wells screened at a variety of depths down to 300 plus feet. They were all monitored for this testing, with transducers. And then basically what we wanted to do was to conduct a series of short-term aquifer tests, no more than 8 hours. And one of them was going to be a shutdown test, because we already have a pumping well, RW3, which is running continuously. So we would conduct a shutdown test there, and then a pumping test in 3 other wells. And these wells typically had open intervals of anywhere from 10 to maybe as much as 25 feet. And their total depths were up to a little over 300 feet. So the screens are relatively short compared to the length of rock that we're testing here. By the way, are there any questions at this point? I haven't heard anything. Okay, jump in if you do. So the objective here was to use the Hsieh crosshole technique and try to define the directional hydraulic diffusivities, and then of course the directional hydraulic conductivities. Between the 4 aquifer tests, we ended up doing 33 independent calculations of hydraulic diffusivity and directional hydraulic conductivity. And basically, we analyzed whichever wells responded to the aquifer test. And they did respond, up to, I think, close to 1,200 or so feet away from the well. We estimated specific storage by using the Tice method, multiple Tice methods. And this is a semi-confined aquifer. And Neuman and Witherspoon do recommend that in semi-confined aquifers, you try to confine your analyses to wells that are relatively close to the pumping well, and then only analyze early time data. And early time means before significant leakage from the aquitard begins to occur. And you can analyze that early time data by the Tice method. And so we get values for that, and we can extract specific storage. So again, we talked about this. The Hsieh crosshole method is going to give us hydraulic diffusivity. We can then convert that to directional hydraulic conductivity simply by multiplying by the specific storage of the aquifer. And we determined that the specific storage in the upper 175 feet of the rock using the early Tice method was 2.4 times 10 to the minus 6 feet to the minus 1, which is right in the typical range you would see for this type of rock. As you went deeper, the specific storage got lower. We went down to 3.4 times 10 to the minus 7th as we got into tighter and tighter rock. So here's this. I'll just show you one example. This is the Hsieh crosshole method. Here's your data curve, and it looks a lot like a typical Tice curve. But in the crosshole testing, you're not particularly interested in the later time data. You can see this goes out to 1,200 minutes or so. You're only interested in the initial, when does the wave of drawdown, in this case it's rebound because this is the shutdown test, when does that wave get there? So you're really looking to match this early time data. You get a match point. It's a lot like the Tice method or any of the other match point methods. You calculate these particular parameters for that match point. And this is the Hsieh crosshole equation with this constant representing conversion factor. But you get the hydraulic diffusivity, which is KD over specific storage. In this case, it's 8.7 times 10 to the 6 feet squared per day. And then to get the directional hydraulic conductivity, you multiply by the specific storage, which I mentioned earlier, 2.4 times 10 to the minus 6. And you get directional hydraulic conductivity. It's basically between this well, the pumping well that is, and this well, which is 901 feet away. we're calculating that the average hydraulic conductivity along that pathway is 20.7 feet per day. And for every well we monitor, for every aquifer test, we get this calculation. And so, for example, here's just a table. This was the shutdown test of RW3, the existing pumping well that we did the shutdown test on. You can see we got distances ranging up to 1,279 feet and also down to, a little over 100 feet. We calculate hydraulic diffusivity, we multiply by specific storage, we get the directional hydraulic conductivity in this next to last column, ranging from quite low numbers to as high as, I guess, 36 feet per day in this one test. For the purposes of analyzing whether this data fits an ellipse, we will typically take the square root of the directional hydraulic conductivity, and that's put in this last column, because that's what you use to form a hydraulic conductivity ellipse. So we've got a lot of this, and I'll just, here's test of BB2. These are the wells that responded to that test. We do the same thing. Another well, EB2. And then we had a deeper well, which was down in the deeper zone, which is below 175 feet. We had 4 more tests that responded. So you get a lot of data. And one of the best ways to analyze that is by doing polar plots, where you plot up, to show you what we're doing here. This is the pumping well in the middle in black. And the green circles are the observation wells. And then we draw a ray from the pumping well through each of the observation wells. And we plot the measured point, the measured value of square root of KD on that ray. So that's what these red plots are. So there's a certain scale associated with, the linear lines that become these rays. And so you plot those measured values in accordance with that scale. And then you seek to fit the best fit ellipse to those data points. So the blue points are the points, as you can see, that are on a theoretical ellipse along those rays. And then you, by varying the major semi-axis, the minor semi-axis, and the angle of orientation, theta, you seek to get the best fit. So the minimum, squared residual, try to get to minimize that and get as close as possible. And this is readily done, using a solver in Excel, or you can use R, and there are other ways you can do this. But you just find the best fit to the data. So here's an example. This is the RW3 well, which had a highly elliptical hydraulic conductivity ellipse, and also highly elliptical cone of influence along that same orientation. You could see that in the data. So this is the best fit to that data. So just to be clear, the pumping wells right in the middle. All of the monitoring wells that responded to the test are shown in blue here. And the dashed lines are the rays going from the pumping well out to the well. And then you can see on the polar plot, we have concentric circles that give us the scale. The scale is each space between, for example, 8 and 9 is 1 and then the square root of feet per day. And so that's what's plotted as the red dots. Those are the actual measurements of the square root of feet per day. And then you seek to fit an ellipse to that data. And this fit fairly well with a R squared of 0.924, which is pretty good fit to the ellipse. And for every test that we do, we end up with a fitted ellipse that gives us not only the orientation of the maximum hydraulic conductivity, but actually quantitatively gives us the K max, the K min, the K mean for that particular test. So there's a lot of data and a lot of useful data. Here's another test of another well where the fit was a little bit different, a little slightly different orientation. And again, you know, the angle of the formations is kind of northeasterly. So this is following the slope and dip strike of the formation here pretty closely. This one had a match of 0.945. Another well was further up. Again, same idea. Plot the values and then try to fit an ellipse to see if it actually fits an ellipse. Sometimes it will not. In this particular rock, we got pretty strong ellipses oriented in almost the same directions each time and with pretty good fits. In other rock environments, you may not get a good fit to any ellipse. And this is the deep well, which had much lower hydraulic conductivities. And I blew it up a little bit so you can see the pumping well and the ellipse. We only had a few points, but they did fit along ellipse. The R squared value is not quite as good, but we can at least see that there's that ellipse in that same northeasterly, southwesterly direction. So here's all the ellipses for all 4 aquifer tests. And, you know, they line up pretty well. This one test here of BB2 appears to have a slightly different orientation, but it's actually data poor on the southeast side. There's really no data points over here. And if you twist that clockwise to the same orientation as these other ellipses to bring it in, you still get a R squared value of something like 0.88, or it's pretty close. So there's wiggle room there because of the paucity of data. But pretty much everything's lined up along strike, which is kind of what you'd expect in this type of rock with the faults. And so, you know, a lot of aerial anisotropy here clearly varied between north 37 degrees east to north 56 degrees east. We had aerial anisotropies ranging from 11 to as high as 178. And that may have been a particular fracture zone that was particularly high permeability. And then we clearly saw that the rock became less permeable with depth, which of course is not an unusual occurrence in this type of fractured rock environment. So I think what we found here is that short-term aquifer tests of really anywhere between 6.5 and 8 hours were more than sufficient to define the hydraulic conductivities of this rock and the specific storage. You know, we think of aquifer tests as, you know, being 24 hours, you know, 72 hours if you're doing a water supply well or something that's mandated in New York State. But when you're doing this kind of fractured rock testing, I don't think you need to be wed to that. You know, you can get a lot of information very quickly by doing 8-hour tests. You do an 8-hour test one day, you let it rest for 16 hours, and you start it up the next day in another test. So you're doing a test every day, and you can get tremendous amount of data with with the transducers, and the data loggers, and very quickly. I don't think you really need to necessarily run for 24 hours with this kind of testing. So the Hsieh cross-hole technique, it's been around a long time, 35 years plus now. And, I've talked to Paul Hsieh about, is he seeing a lot of application of this? And he's not. And nor am I. I mean, I do a lot of reviews of aquifer testing, because I taught it for years at Manhattan College in Columbia. I haven't seen anybody use it. I use it all the time. I think it's a really valuable technique for mapping 3-dimensionally hydraulic conductivity. And I think we're only catching up to being able to, model the results of all this data we get back from this. The other thing I wanted to at least mention here is that this method also works in porous media. So it's not confined to fractured rock. This was a site where we used the same Hsieh cross-hole testing in the Englishtown aquifer. And we had lots of monitoring wells, so we could see how fast drawdowns spread out in all different directions. And we were able to basically map the hydraulic conductivity within the aquifer with a pretty high degree of accuracy because we had so many monitoring wells. So this is, and I worked with Chris Wenzel at another site, he'll know what I'm talking about, where we did this to a buried glacial outwash aquifer, where there was a buried valley, and the Hsieh cross-hole technique worked excellently to map the hydraulic conductivities within that buried valley. We found directional hydraulic conductivities of as high as 2,000 feet per day in the basal gravels of that glacial outwash valley. So I just wanted to mention it can be used also in porous media aquifers, and it can be really useful in mapping 3-dimensionally the hydraulic conductivity of the aquifer. So let me jump again. Any questions? At this point, I was going to turn a little bit of attention to tracer testing.
Yes, we actually have a question in the chat.
Okay.
What are the units of anisotropy? I'm going to mispronounce this, anisotropy, and how is it defined in the context of the 8-hour tests performed?
Well, anisotropy is defined as a ratio. So it's the ratio of hydraulic conductivity in the K max direction, that would be in feet per day, over the K min, so the minimum hydraulic conductivity, which is often orthogonal to the maximum. So it's feet per day over feet per day, so it's unitless. It's just, you would say the anisotropy, is 100. It's a ratio of the K max to the K min. And then it also has an orientation, a directional if you're looking at an aerial anisotropy. And in a vertical anisotropy, you're looking along a cross section, and there's a direction there. And it's usually the K max direction will be parallel to the bedding, being controlled by whichever layer has the highest hydraulic conductivity. And normally the lowest hydraulic conductivity is in the direction orthogonal to the bedding. Does that answer the question? And I think it was Terzaghi who said, if you know nothing about a hydrogeologic formation, assume it has a vertical anisotropy of 10. Most formations, certainly sedimentary formations, alluvial formations, are going to have anisotropy, vertical anisotropy of probably at least 10. When we're doing mathematical modeling, we put 10 in, as a routine number. And if we have better data, we'll change it. But usually 10 is the default value for vertical anisotropy. Okay, let me continue on. I wanted to mention tracer testing because what's called the convergent flow tracer test is a very cost-effective way to get some good data on fracture porosity, and which will help with definition of seepage velocity in a fractured rock. So in a convergent flow tracer test, you're basically just doing an aquifer test. So if you were doing an aquifer test where you had a single well and you're pumping it and you're measuring drawdown in a series of wells at varying distances from that pumping well, what you do is in a well reasonably close to the pumping well, shortly after the well begins pumping, and it'll fairly quickly establish a quasi-equilibrium in and around the pumping well. So you might run for half an hour or an hour, and then inject into an observation well a suitable tracer. And so just create a small cloud of tracer and have the pumping well pull that from the injection well to the monitoring well and observe its appearance in the pumping well. So you're not really adding that much to an aquifer test. You're doing all the, transducer monitoring anyway. All you're doing here is adding an injection of a tracer into an injection well or a monitoring well, and then awaiting its appearance in the pumping well. So basically, just think of it as if you have an equation, the pumping rate times the time is a volume of water that you've pumped. And what you're basically saying is that all of this water within this cylinder of depth D and radius R, that volume of water, first of all, that volume first multiplied by the porosity would be all of the water within that cylinder. And so that's how much water you're pumping out of the well at the time that this tracer cloud moves from this well to this well. So at the same time, all of the water that exists at the beginning of the test around the perimeter of this pumping well all converges on and arrives at the pumping well at the same moment, because it's an inward radial flow heading, right toward the pumping well. And you can use that to write a simple equation. This is how much water we pumped, our pumping rate times time when the tracer appeared. And this is the volume of water in that cylinder. Pi r squared, it's the area of the circle, times D. I'll just go back. So it's the area of this circle times the depth D. That's the total volume of the cylinder. And then multiplied by the porosity, in this case, the fracture porosity. And solve that equation for N, and you get a very simple equation. QT, pumping rate times the time until the tracer appeared, divided by pi r squared D. And you know all these parameters within some degree of accuracy. I'll just show you, this is a test from quite a few years ago. It's occurring at the Seneca Meadows landfill up near Syracuse, that area. At the time, it was the largest operating landfill in the state in terms of, tons of solid waste being received every day. And this was all part of an expansion of the landfill. So this is the pumping well. It's screened in the Onondaga limestone. And there are wells, dozens of wells all over. The drawdown from this, we pump 22 gallons a minute. The drawdown spread out several thousand feet in monitoring wells all over. There's a monitoring well just out of sight here behind this tank, which is where we injected the tracer. And we used a rhodamine WT, and we mixed it up in a drum, and then used a peristaltic pump to pump it down into the screened interval of that monitoring well. And I was trying to set this up so that I would get enough of the tracer showing up that I'd be able to see it and see when it arrived. But I'm also monitoring the water. But here's the water being pumped out of the drum over into the well, and then that tube goes all the way down into the screened interval of the well. So we're pumping it right down into the screened interval. And all right, then we start running. So this is a little side stream of water coming out of the pumping well, and I'm taking samples of it, but I'm not seeing any red. So, I'm getting a little nervous about this test. We're running this for 24 hours, and I never saw any red. So I kind of thought that somehow we blew it on this test. And it's one of the harder things to decide on, by the way, is how much tracer do you need to put in? Because there are factors that influence how much of it's going to make it through to the pumping well. Things like matrix diffusion. You might get a lot of diffusion of the tracer into the pores of the rock. In any case, I religiously kept taking samples all night long for future laboratory analysis. We put, in addition to rhodamine, we put in what was it? Bromide. And we measured specific conductance too with a meter. We didn't really see much of anything happening. So, I didn't know whether this test worked or not. But when I got the analytical data back, there it was. The red line, the red dots are the rhodamine. And it came in up to about a little over 9 parts per billion. So it's not visible at that concentration, but it's very clearly there. Really nice curve, jumped up, and then tapered off, as it often does, due to things like matrix diffusion and so on. And you can even see a little of the bromide. You can see the bromide not as distinctly as the rhodamine, but you can see it. It peaked up and it tailed off. And you can see here we were pumping 22.5 gallons a minute. The injection well was 36.7 feet away, and the aquifer is about 80 foot thick at this point. So it worked. It actually worked quite well, and to my relief, because I wasn't sure it worked at all. And then using that same equation, plugging in the pumping rate, it showed up at 280 minutes. And then the other parameters, we get a porosity, a fracture porosity of 0.0025. That, by the way, is right in the middle of the range of fracture porosity that you typically see in sedimentary rock. It's almost always 2 zeros something in that fracture rock. And I just listed a program here which is helpful. It's more recent, but it helps you plan tracer tests of this type. But I will say it does not take into account, at least at this point, matrix diffusion. So loss of tracer as diffusion into the matrix of the rock is not taken into account in this. I'll show you one more here. This one was a little more complicated because the aquifer is aerially anisotropic. So there's, rather than a circle, there's an ellipse. So it's pretty simple to take that into account, and I won't take too much time with this. And I'll show you the equation is very similar. It's calculated the same way. You know, an ellipse, the area of an ellipse is pi times the major semi-axis and the minor, half the minor axes, times d, and then times porosity. So you end up with a very similar equation, but you do have to fit the ellipse to it. So this was a test that was done up in Canada in a limestone formation. It's kind of a, so I remember, Middle Devonian, I think it was the Delaware and Anderton formation. The pumping well is here in the back. Can you see my pointer? Chris, is that when
Yes,
I
we
move?
can see it.
Oh, great. Okay. So that's the pumping well. This is the injection well. We actually had, because this well is so close to the pumping well, we had a packer set up in this well above the well screen. So this inlet tube carrying the rhodamine WT, and this jug here has water in it to help flush the rhodamine out of the well screen. So you pump this rhodamine in first, followed by the water to just make sure it gets out into the formation. But we had a packer set up there to make this well more responsive to drawdown. And that's another story, but you know, in this type of rock, you can get drawdown occurring so rapidly in the formation that a well can't keep up with it. It's not responsive enough, but a packer will make it almost like instantly responsive. So this is the test setup. We were offered one opportunity to discharge the water directly to the Detroit River, but I didn't want to do that. I was a little uncomfortable with that idea. So we were injecting it about 1,500 feet away into a waste quarry where tailings are dumped. I'll show you that. So here's the setup. This is the peristaltic pump, taking the rhodamine WT, and in this case, I put a lot more rhodamine WT. The last time as I showed you, I never saw it, and I was fortunate that it came in at 9 parts per billion. This one is loaded up quite a bit higher, and it's being injected with the peristaltic pump down into the well, under the packer, and into the well screen. And we injected all that tracer.
We actually do have a question about how much rhodamine do you use?
Yeah, that's a great question. You can try to calculate it, but it is difficult. I mean, I like to get, you know, first of all, you have to treat it some way. A recent test we just did this past year, we're in a very sensitive environment, so we had to run the discharge through carbon in order to treat it. So you want to make sure you're not going to overwhelm the carbon, but you want to make sure you have enough in there to be visible and concentrations of a suitable level. So, you know, I typically like to have part per million levels, you know, maybe up to 50 part per million. You can see it down to, I think, about 100 parts per billion. You can see a little bit of the tracer. So when you're in the part per million level, it is visible. So that's nice. I like it to be visible, but it also has to be treated. So you got to make sure the carbon will treat it. And here we didn't have to worry about that. It was going into a waste pit. We got approval to direct discharge. You can see way in the back there is where we're doing the pump test. And this is the discharge line coming up and goes into this tailings pond where they dispose of their tailings. So here's the law. It's about 100-acre old quarry that they're filling with tailings, which is largely calcium sulfate. And it's discharged over here. This is our discharge right here from the well. We were pumping 105 gallons a minute, as I recall. And this is into they actually recycle this. It's basically gypsum. So people when it dries out a little bit, they'll dig it out and recycle it. And this is one of the pits I think the stuff was dug out of. So that's the plant's discharge. It's something like 3,000 gallons per minute of tailings being discharged out into that pond. And then we're running the aquifer test, and we've got a fluorimeter here where we can measure the rhodamine concentrations. We've got jars where we can take some samples for chemical analysis if we need them. So we can read right off this meter what the concentrations are in this water, which is nice. Yeah. And here is the first appearance of the rhodamine in our discharge, starting to dye that pond pretty red. Eventually it looked like that. So we had plenty of rhodamine in this one. I think you could see this pond from space, but it's right in the middle of this waste disposal area. And this is what happens when it mixes with those tailings. The tailings just kind of eat it up. You know, it just gets lost in the tailings, as you see there. And there it is. It's just being the red is just being assimilated within the white, pretty much gypsum material that's being discharged. This is actually a hydrofluoric acid plant, and they end up with a discharge of gypsum. So here's the results. It came through pretty fast. We injected it over about, I think it was 30 minutes. So this is like, this black line is the centroid of the injection mass. And then this is roughly the centroid of the peak of the tracer coming out in the pumping well. And so here we had concentrations. I did say I loaded it up. It had in the peak, at the peak, it was a little over 800 micrograms per liter. So that's parts per billion. So it didn't quite reach 1 part per million, but it was certainly very red. And then it tapered off pretty quickly. A little bit of tailing, which I think is probably indicative of a little bit of matrix diffusion into the limestone. Or it could be tracer getting hung up in the well interval a little bit and coming out more slowly. But it came at a pretty nice peak, 62 minutes. And there's that same equation I showed you earlier, in this case for an anisotropic condition. And this is our pumping rate, 14 cubic feet per minute, which is 104 gallons a minute. Peak came through 240. That's how long we pumped. And we got a porosity of 0.0045 for that limestone material. So that's it on tracer testing. I think it's a very useful and not expensive test to do while you're doing an aquifer test. It's just the natural, because you're not going to lose tracer. The tracer is going to come into your pumping well. You're not going to lose any. Natural gradient aquifer tests are tough because you can never really be sure that the tracer is going where you think it's going. But in this test, it really doesn't have much choice. It's getting pulled radially right into that pumping well. And so you know where it's going, and then you can measure how long it takes to get there. But I think where we're heading, maybe I can speculate. I think we should put more emphasis on more shorter term aquifer tests, particularly in fractured rock. There's no reason to do long-term tests unless you're trying to build a water supply well or something. If your objective is measuring hydraulic conductivity and specific storage and understanding the three-dimensional extent of the aquifer, you can do these short-term aquifer tests quickly and inexpensively and get a lot of good data nowadays. The other thing, and Chris and I worked at a site, Chris Wenzel and I, where we were able to do this. There was an existing public water supply well that was pumping from a deep glacial outwash aquifer. And it ran alternately, it turned on and off to supply the needs to keep the supply tank full. So it would go on and off on kind of a regular basis. And we could see the drawdown and rebound associated with that water supply well throughout the whole aquifer, to up to almost a mile to the north. We could see every time that well turned on and off, and that's a natural for the Hsieh cross-cell technique. So you don't even have to do the pump test. Just let the water supply do the work for you. Put the transducers out and gather the data. So I think this technique is really useful, especially in fractured rock, but this is an example of where we used it in a glacial outwash aquifer and literally mapped the hydraulic conductivity spatially throughout the formation. So it's useful in porous media as well. And if it's applicable, if you have enough monitoring wells, you might be able to map the three-dimensional hydraulic conductivity ellipsoid. And that's like the holy grail of fractured rock definition. But that's not always applicable. Sometimes it's just helpful to understand what could be called the architecture of the aquifer. Where are the high permeability zones? Where are the low permeability zones? And that's really useful. And I'll just throw in another plug for doing tracer tests because it's very useful to understand the fracture porosity and correspondingly the actual velocity of groundwater that flows through the rock. So I'll end there, and I'm happy to take any questions that people might have.
Thanks, Bob. That was a lot of great information in a very short time. A little overwhelming for me, but I'm sure a lot of others were able to follow that pretty well. We have a couple of questions already in the chat. If anybody else has questions, please feel free to put them in the chat, or you can unmute yourself after these first couple of questions. So the first question is, do you recommend recovery testing versus drawdown testing for aquifer testing, given it eliminates mechanical influences?
So do you mean, when you say the term recovery, do you mean like a well shutdown test?
Does the person that put that question in have a response to that?
Yeah, or are you thinking of recovery like a slug test? I can't quite hear anybody.
Yeah, I don't have a response to your question on the question.
Okay.
Do you think there's a
I'll try to
ahead.
answer it. I'm not quite sure what the questioner means by recovery testing.
They did kind of clarify recovery testing, not slug testing.
Not slug testing. So, I mean, I am a fan of well shutdown testing. So in other words, if you have a site where there's an existing well that's continuously pumping, maybe it's a remediation well, it's capturing a plume or something. You can just do a shutdown test, monitor all of the wells that might be influenced by that operating pumping well, and then make sure you know what the pumping rate is. You need to know the pumping rate, and then just shut it down and let the aquifer rebound or recover due to the cessation of pumping. I think that's a great way to get good data, and it doesn't matter whether it's drawdown due to pumping or rebound due to a cessation of pumping. Either way, you're going to get data that you can analyze. So it's perfectly fine and probably cheaper.
Okay. That's an important one.
Yeah.
All right. Their other question is, what about moderate capacity? DOH wants to show sustainability. Do you overpump to eliminate storage effects?
Okay. And I think by storage effects, do you mean well bore storage? That is water that's within the well bore? If it's let's say it's a 12-inch diameter well, there's a lot of water in there. And if you pump it at a very low flow rate, at least initially, a lot of the water that you're pumping out of the well is water in storage in the well. There are methodologies to account for that and take it into consideration. But if you pump it at a higher rate, if that's possible, you can eliminate that problem fairly quickly. But that is a factor that you need to take into account, especially if it's a large diameter well. Like I've seen wells that were 3 feet in diameter. You pump a well, let's say a 3-foot diameter well that's 30 feet deep, there's a lot of water in there. And if you're only pumping at 1 gallon a minute, let's say, because you think that's the sustained pumping rate of that well, it's going to take a long time to pump all that standing water out of the well. So you need to take that into account when you analyze the data.
They did add an additional comment.
Okay.
Plus dewatering lower yield fracture or bedding zone intervals. This is more applicable to production wells in bedrock settings.
Yeah, that's in fractured rock with a well that is screened across most of the aquifer. So a long screened well, as you pump the well, you will begin to draw down water levels, which will, in the well, will go lower than some of the water-bearing fractures. So as you're pumping the water level down, the water-bearing, let's say water-bearing fracture A is below the water level in the well, and the amount of water that's flowing out of that fracture will be a function of the water level in the well. But once the water level reaches that actual water-bearing zone A and starts to fall below it, the water will still be coming in, but it'll no longer be a function of the elevation of the water in the well because it's dropped below the fracture. So it'll continue to drain out and may eventually reach kind of an equilibrium seepage rate into the well, or it may dry out. So that's a complication in fractured rock wells. If you pump it way down, you're going to dewater a lot of the water-bearing fracture. So they'll first become not a function of water level any longer, and eventually may dry out. So that's a significant issue to deal with. I could try to give you a longer answer to that, but it would take quite a while. It's just something you have to deal with.
Okay, got a couple more questions.
Sure.
In the case of the Seneca Meadows pumping and tracer test, do you feel advection and dispersion could also account for the attenuation of the observed rhodamine concentrations, or was this considered and found not to account for observed attenuation?
I don't think it's advection and dispersion. I mean, that's those properties are happening. The water, the plume that is migrating from the monitoring well is subject to advection, in the flow field that we've created by the pumping. And it is no doubt dispersing a bit as it flows that 37 feet. But we're capturing it all. So we're pulling it back in again. So we're getting that water. I think most of the attenuation or that causes the tailing, each of those curves I showed you, the back side of the curve was flatter than the front side of the curve. So the curves went up very fast, but then they tailed off. And I think that's due to a couple things. One is matrix diffusion. So you're actually losing mass from the flow field. The flow field is fractures. The tracer is flowing through the fractures, but it's also diffusing into the adjoining matrix of the rock. And so you're actually losing mass, at least for the short term. So that's number one. Also, if you're not careful, and that's why I showed that one jug of clean water, it's my practice to, after we inject the tracer, to then typically inject maybe 2 times as much clean water back in to make sure we've got most of that tracer out into the formation. So that's a factor too. You get some mass that just hangs around the well bore and maybe more slowly leaks out, and that causes, I think, some of that tailing.
Okay, we do have a couple more questions, but I know we're going a little late today. Chris, do you want to continue going through a couple more questions, or
I'm good.
should we have...
I'm fine. Yeah.
Okay.
Whatever you want to do.
Yeah, hit a few more.
Okay. All right. Short-term tests are great because they reduce costs, but longer-term tests can identify boundary conditions that may be important to understanding the overall aquifer conditions. Is this an issue in relying only on short-term tests that characterize aquifers close to where the stress is applied?
Yeah, that's a good point. There are some aquifers that may have boundaries. And in fact, the one I mentioned, the Buried Valley up in New York State, is a very laterally defined channel filled with gravel and sand. And it's cut and eroded into a moderate to low permeability rock, which forms a boundary on either side. And in some of the aquifer tests that have been done there, we've seen the rebound. I mean, I'm sorry, the boundary effects of the drawdown, in a sense, bouncing off the rock walls and rebounding back into the aquifer test area. So that is a factor if that's something that you may be dealing with. And that may be a reason why you could want a longer test. Most of the water supply aquifer tests are going to be a minimum of 24 hours and more likely 72 hours or more, just by regulation. But if you're working on a contaminant site and you need to get a lot of information about hydraulic conductivity and storativity, then I think there's an opportunity to do shorter term tests.
Okay, thank you. We have one last question in the chat.
Okay.
Can the Hsieh technique also be used on semi-confined or unconfined aquifers?
Yeah, that's a great question too. Semi-confined, yes. Water table aquifers, not so much. I mean, it was originally developed for semi-confined or confined aquifers. The problem, just from a practical perspective, is a water table aquifer, the storativity is defined as specific yield. So you have a much higher storativity and quite a variable storativity. So it's hard to lock in on what the specific storage is, because it's a combination of essentially specific storage, but also aquifer dewatering. It's a water table aquifer. So it doesn't really lend itself to testing of water table aquifers.
All right, thank you very much, Bob. Chris, you have
You're
the
welcome.
quiz ready?
I sure do.
So do I hang on here, Chris, or am I completed here?
Well, hang on for the quiz.
Okay.
Make sure that we get it right.
Yeah, maybe there's some questions too.
Yeah. All right. We should be sharing the screen.
Yep, we see your screen.
Yeah. Okay. All right. 3 questions. If you care to answer, you can answer. When you put your answer in the chat, just put it like 1A or 1B or 1C, whatever. Okay, so the first question is, converting the hydraulic diffusivity given by the Hsieh cross-hole technique to the directional hydraulic conductivity requires that one divide by the specific storage, multiply by storativity, multiply by the specific storage, or divide by 7.48. I'll give you a second to throw your answers out there.
They're
You
actually
should-
coming
Go
out
ahead.
on the screen here. I can see the answer, so can everyone else, I think.
Well, it's a multiple choice, but you did mention this exact
Yes, I
question
did.
twice.
I did. Yeah.
All right.
Well, it may not. Maybe I'm not. Maybe I'm not seeing it right. I'm seeing answers pop on the screen, but I may not be seeing the entire answer. I don't
Oh,
know.
well, yeah, you didn't give me the answers. I had to figure it out for myself. But, so the answer should be C, multiplying by the specific storage. Correct, Bob?
That is correct.
All right, good. All right, next question. Pumping of an aerial pumping of an anisotropic aquifer would produce a circular cone of influence, an elliptical cone of influence, an irregular cone of influence, or no cone of influence. Give you a second there to throw your answers out. Should be pretty easy. Well, folks, the answer is B, an elliptical cone of influence. And the last question, the Hsieh cross-hole technique is not applicable to porous media aquifers, only to fractured rock geologic systems. True or false? And I think that one's pretty easy. It's obviously false. Bob pointed out more than one example where you applying that technique to a unconsolidated formation produced really great results. So there you go. That's it on the quiz. I think, let's see. I don't think there's anything else we need to cover here outside of thanking Bob very much for doing this, and we really appreciate it. It was knocked it right out of the park. And
Well, I hope it was useful, and I look forward to seeing some of you folks at some other event of this LIAPJ.
you're always welcome here.
All right, thanks.
All right, folks, I think that
Take
concludes
care.
it for the evening. So